we need to now look at intermolecular attractions, and there's basically three categories. And the first one of those categories is London forces. And London forces are created, they're also called van der Waals forces. These forces are created between two molecules that are nonpolar. And so if I have a nitrogen bonded to another nitrogen, what happens is they will have a slight, very slight attraction for another pair of nitrogens, and you get this van der Waals or this London force between these two molecules. And we'll move on and look at those in just a minute. The next one we have is a dipole-dipole, and a dipole-dipole attraction is something like a bond between something like hydrogen and chlorine. What you get is electronegativity difference between these two. Electrons are tending to move in that direction, making this slightly negative, making this in slightly positive. And what we have is another hydrogen, chlorine, electrons moving again in that direction. So what we get is slightly negative, slightly positive, and there's a attraction between that chlorine and that hydrogen. And the last, but the strongest of all of them, is the hydrogen bonding. And we will go into how water actually bonds to itself, and we'll look into those different types of bonding. So the first one we're going to start out with is London forces. And in London forces, you have two nonpolar molecules, or you have nonpolar molecules. You have a thing called an instantaneous dipole and an induced dipole. And what I have here is if you look at these sets of molecules down here, you have attractions and you have repulsions that are continuously going on, trying to figure out how these are going to actually attach together. What's created is this instantaneous dipole, and what that means is an electron tends to move, or an electron density tends to move in one direction and slides over here and makes this in slightly negative. And what that causes is the molecule next to it to be induced, and its electron density moves to the other end. Now, the molecule doesn't feel comfortable that way, or doesn't like to be, is not real stable that way, and so what you get is the one that was induced now becomes instantaneous, and its electron density moves the other way, causing this atom to be induced and the electrons move. Now, in London forces, the smaller the molecule, the less attracted those molecules are to one another. The longer the molecule we get, the more they tend to stick together. Even though they're nonpolar, they tend to bind together. I always think of it as small molecules would be like rice, and how well it's dry rice sticks together, as opposed to looking at something like long spaghetti. The longer the chain, the more they kind of intermingle and hold together. And so those instantaneous and induced dipoles are created between those nonpolar molecules. Now, a dipole-dipole, in this particular case, what we have is we have some hydrogens all the way around here, all the white ones, and this is a carbon in the middle, and then this end piece is a chlorine. And if you'll notice, we have electronegativity of 2.1 and 2.5 here, and so between the hydrogens and the carbon, the electrons are moving in towards the carbon. And so what happens out here on each of these hydrogen is they all become slightly positive. On the other end, if you go 2.5 to 3, the electrons in this bond are tending to move closer to chlorine. And so this end becomes slightly negative. And so we have this positive end down here, we have a negative end up here, and so we have this polar molecule. Well, the next, this is called methyl chloride. The next methyl chloride is also has the same kind of structure, and so what you get is you get this intermolecular attraction, or this bond that's created between these hydrogens that are positive and this chlorine that are negative, and they tend to stick together fairly well. And so dipole-dipole is created between polar molecules where they have two magnetic poles, a positive end and a negative end, and they tend to stick together just like a pair of magnets do. The last one is this hydrogen bonding, and hydrogen bonding is created for example, this piece is water right here. And what you have is an H2O, and it's bent, and that oxygen is slightly negative, and those two hydrogen are positive. Well, the attraction actually occurs between this hydrogen of the next molecule and the oxygen of this molecule because of their positive and negative charge. Hydrogen bonding is caused because of the degree of polarity that is caused between this hydrogen and that oxygen. If you remember, this is 2.1, and I think this is 3.5, so we get a 1.4 difference. And this 1.4 difference is extremely polar, and so because of how extreme it has a great magnetic attraction. Now, hydrogen bonding only occurs when hydrogen is bonded to a nitrogen, hydrogen is bonded to a fluorine, or hydrogen is bonded to an oxygen. And so in those three cases, if we're bonded to one of those, the next molecule over, what you're going to have is, for instance, if we do NH3, and I draw another NH3, oops, start out with my H, what you get is the hydrogen bond between that nitrogen and the hydrogen of the next molecule. And, we could get this one also. And so we have this attraction between those nitrogen and those hydrogen. Okay, for example, this is water doing hydrogen bonding. We have this attraction between a hydrogen and an oxygen, hydrogen and oxygen, and all the way around. And this actually helps us bond things together. Water beads up really nicely because of this hydrogen bonding. Now, this particular one is basically looking at a polymer, or also could be a DNA, how a DNA strand holds together. We actually have this hydrogen bonding that's created. Notice hydrogen is bonded to nitrogen, and then we have an attraction over to an oxygen, and so we get that bond right there. And the same thing happens all the way through here. And so we have this interlacing of all these molecules causing hydrogen bonding. So the strongest bonding, if we want to go over it real quick, if we flip back a couple pages, the London forces or van der Waals forces are the weakest. So these are weak. Dipoles, second strongest, and then hydrogen bonding is the last, and it is the strongest of the three types of intermolecular attractions.